Hi, everyone. Welcome to this week's seminar. We are welcoming Dr. Brennan Phillips from URI. He received his BS in ocean engineering from URI, then went to get his MS from UConn in oceanography before returning back to URI for his PhD in oceanography. And prior to joining the faculty, he was a postdoc fellow at Harvard Microrobotics Lab. He was also an ROV engineer for the Nautilus. And he specializes in development and application of novel instrumentation for oceanographic research. So I'll hand it over to you.
Thanks. All right, so a couple disclaimers. First, I just switched to a PowerPoint, so things might be a little out of order. I converted from Keynote because I live in Macworld. So I'm gonna be a little awkward as I go through the videos. Second disclaimer, most of what I'm showing here today, I have not shown yet. So my slides are a little fresh and I haven't had a chance to get through it. So sorry, you're the test batch here, but it is kind of cool to see new stuff. I'm really excited to talk about some of the work. So kind of an audacious title, but essentially I'm going to present some of the work I've been doing for the past 2 years or so down at URI, give a little bit of background leading into it before we get into the meat of that. I know there's a Q&A, but if you have a burning question, I have no problem. Certainly, I don't know about the mic, but if you have a quick question or some clarification, I certainly have no issue if you want to raise your hand, and I'll address it as we go along. This image right here, I'm actually not going to talk about this any later, but one of the themes I'm going to get into is sort of using non-traditional platforms enabled by using smaller, cheaper robotics. And so this trip was in June this past summer in the Solomon Islands on a tugboat that we chartered out there, and we're doing deep sea winches, ROVs, net tows. It was a really interesting trip, I'll say that. You really start to appreciate what a real oceanographic vessel is after you work on a tug. But there is beer at the end of the day, which is kind of cool. Whatever you bring to go with it. And you get to work in really odd places of the world where big boats aren't necessarily going. All right, so my lab now at URI is called the Undersea Robotics and Imaging Laboratory, or the URI-L. Yep, shameless. And I encourage you to go visit the website if you're interested in learning more. Everything on the website has things that are already published. So none of the stuff today, most of the stuff up today is not really on there yet. So if you want to dig deeper in background info, you can find it all there, plus some field reports and images and that sort of thing. So just a few highlighted shots, a couple members of the lab. I'll talk about them in a minute. We work on, we're platform agnostic, so it could be, an ROV, a sub, some platforms we build ourselves, AUVs, whatever. We're building sensors and all that sort of thing to go onto whatever it is underwater. And just a really awesome image to flash is this Vampirotuthis since Halloween. That's the vampire squid at, I think, 1,500 meters off the Revillagigedo archipelago. I can't even pronounce it, in Mexico, filmed with a low light camera. Folks in the lab, we have 4 PhD students so far, a master's, soon to be PhD, because I've convinced him, working there. So we have Brendan, Rendy, Russ, and Alex, and a bunch of undergrads as well. So I rely heavily on undergraduate support to work in the lab. Carla and Nick are mainstays. Maddie's coming up, has been working in there. And we have a few other folks that join per semester as we go along. So we're growing, which is really great. And things that we work on, in addition to everything today, it's pretty broad, as you're going to see. I have a broad range of interests, and I'm getting myself into trouble with that. But to boil it down in a few bullet points, we're a deep sea robotics and imaging laboratory. We're interested in samplers. We're interested in soft robotic control systems, ways to control soft robotics. That's my end of that. We're interested in low light cameras, and that gets into themes of bioluminescence and biological avoidance. We're interested in low cost, simple platforms and imaging systems. So that's something I'm really going after. If it's cheap and deep is sort of the lingo there. And then lastly, we're getting into fiber optic distributed sensing, and I'll talk a lot about that in a little bit. All of that is done with a field test and hopefully a scientific application in mind. So we're not just building something in the lab and then writing the paper. It has to at least work at least once, hopefully, multiple times offshore. And so I collaborate heavily with other oceanographers and marine biologists. And again, we use deployment platforms regardless of what it is, ROVs, drop winches, freelanders. We have a lot of that in the lab, or we go out and collaborate to get onto those platforms. So I actually gave a seminar here about 3 years ago, and a lot of it focused on being stealthy underwater. And I talked about avoidance effects from ROVs. And that's the preface really to the topics that I'm going to talk about today, sort of the driving force behind it. There's one other image in there. As was mentioned in my intro, I used to be an ROV pilot. And so I used to fly Hercules up there in the upper left-hand corner. I've worked with most of these ROV systems here. These are industrial robots, right? Who's been out to sea with one of these vehicles before? A lot of you? Yeah, they're amazing systems. I'm not trash talking them, but I want to put them in context with what we're doing underwater. They're amazing systems. They're super sophisticated, right? Studded with sensors, so much data coming off of them at once. You get to sit up top with all your best friends and enjoy the show. It's a really great thing to do. But in order to get good images underwater from one of these vehicles in the deep sea, you're blasting a lot of light underwater. And they also have manipulators on them. And often the thrusters themselves are also hydraulically driven. The manipulators are hydraulically driven too. That means they have to have something called an HPU, or a hydraulic power unit. And those things are very noisy. If you've ever heard one of these things run on deck, it's kind of excruciating on your ears. And underwater, they produce a lot of like loud, dirty, low frequency noise that travels really far. The lights though are sort of the biggest offender. So I've been sort of making my little cartoon diagram of ROVs and how many lumens they output. One vehicle that is not on there is the Schmidt Ocean Institute vehicle, Sebastian. It's actually 300,000 lumens I calculated a couple weeks ago. So I need to add that up there. But so 300,000 lumens there. Deep Discover's pushing over 200,000 lumens of light output. Doc Ricketts and Mbari is in the hundreds. And then our other three, Herc, Jason, and Ventana, our favorite science ROVs, are all in the 100,000 lumen output range. So all of these essentially are equivalent to like a Little League stadium underwater. That's how much light these things are putting out at night. That is quite disturbing. So the plot I've been carrying around a lot for years is this one. I have a lot more of these now as of a couple weeks ago, looking at ROVs and how they disturb the scattering layer. So I'm not going to spend too much time on it because I want to get into the meat of the presentation. But this was taken off the Okeanos Explorer several years ago. They were out in the Pacific Ocean and they were trying to do a midwater dive to look at these backscatterers, these animals in the deep scattering layer. And the first thing, this is the ROVs, or the two vehicles in the water, Sirius and the Deep Discover. And they're going down to try and reach this layer that they originally saw on their EK60 fisheries echo sounder. Sure enough, the vehicles go there and the scatterers go up and away. Then they say, oh, let's go back up there. They move the vehicles up and all the animals move below them. And then they retrieve the vehicles and give up and they go back to doing what they were doing in the first place. And we have repeated casts like this. It's hard to find a ship that runs both ROV and EK60 or EK80 at the same time. But I have a bunch of, like a library of these things put together at this point that just show clear avoidance from the vehicles. And it appears to be light, is sort of the biggest thing. So the takeaway from all this is that these big industrial vehicles are quite disturbing. And that has pushed me into the topics that I'm going to talk about today. And eventually I want to build an awesome vehicle that doesn't do any of that, right? So 3 acts. Oh, yeah, see right away, that's the PowerPoint going on us. But Act 1 is deep sea soft robots and how to drive them, really, is the focus there. In Act 2, most of the presentation, I'm going to talk a lot about 3D printing and how we can apply that to deep sea robotics. I got a printer in my hands and I went nuts. There's all kinds of cool things we've been able to do. So these acronyms will go through, but rad sampler, DeepPy, pressure housings, and SLA printing at sea. And lastly, I want to talk about fiber optic distributed sensing for oceanography as our third portion of the presentation. Yeah, so you'll know what most of these are by the time we're done going through that. So deep sea soft robotics, who has not heard of soft robotics? It's okay if you haven't. Most people know now, yeah, because it's like a few years. It's sort of this has come up as a major research topic in engineering. Soft robotics is the whole idea of using compliant materials, essentially like fancy balloons, inflatable actuators to gently grasp and manipulate underwater. So this is an early gripper that we built up at Harvard to grasp a holothurian. I forget how deep it was, at least over 1,000 meters. And this is run off the Hercules ROV to grab these things. You can lift and grab and give them a hug and let them go if you want to. Early work started with things like that and using a vehicle here. This is a Falcon ROV. which is an off-the-shelf vehicle that we've highly modified. And to actuate the fingers here, we actually attached them to the end of a Hydraulic standard manipulator. So this is something you would see on, well, most people who own a vehicle like this have a manipulator like this. And we modified that hydraulic system essentially to push a volume of seawater as controlled as we could to produce the pressures needed to actuate these fingers. So these fingers here actuated about 15 to 20 PSI. Most hydraulic arms like this are pushing 1500 PSI. So we're using a large hydraulic system to drive a much lower pressure system, and it's inefficient, big and heavy. This whole payload is basically driving these fingers right here. It's a whole mess. So it worked, but we wanted to do better. So I'm going to try and skip through some of this real quick. We then moved on to making a soft manipulator, and a bulk of my postdoc work was building a hydraulic engine that you see here to drive multiple channels of soft actuators. So in a minute, I'll play the video. The way we got around that was we removed the hydraulic power pack altogether, the HPU that was driving the low pressure seawater, and instead used a McLean deep sea pump. So anybody use McLean Labs equipment, we just use one of their pumps. They're used in a bunch of different systems like sediment samplers. What are those things you called? When carbons are sinking down, I can't think of it. Oh, sediment trap. They're in sediment traps and that sort of thing. So we repurposed this pump to produce pressure to fill up an accumulator here. So we had a little bit of a volume that is then hooked up to a large manifold with all these different channels. And we can run these different channels for different actuators. So this is, again, quite a complex, fairly large rack system. So if I hit play and then I skip ahead, I don't want to have you sit through all of it. I actually want to get to this part. Yeah. So pay attention to how slow that is actuating, right? And the first version I showed you earlier, the first grippers were actually even slower. It's excruciating to watch. You get it over an animal, say close now, and we all sit there and wait for 10 seconds as this thing slowly goes and closes. So does it work? Yes. Did it work at depth? Yes, but we want to improve upon that. So where we are now, sorry, yeah, that's how that system was laid out. Sorry, before I get there. This basically walks you through how that system was laid up. You have a pump, control bottle with some electronics, the accumulator, the manifold, and in hydraulic speak, those are the symbols, right? Pump, accumulator, and the manifold to go on there. So one great thing about this about this system is that we could pressurize to up to 50 PSI, and pressure equals gripping force, right? But we can only vent afterwards with this system is one problem. We could produce pressure with the pump, but we couldn't back drive the actuators to open them up. We could just release pressure and they would slowly go and release off. And we had a very limited flow rate out of this system too. So we weren't able to go very quickly, right? That's the main takeaway from that video earlier. So where we're going now is something funded by NOAA Office of Exploration and Research. I don't know what to call it quite yet. It's an oil-filled linear actuator drive system. And it's quite simple. This thing is a little bit bigger than a bottle of wine. And it's based on a Festo high-speed linear actuator. If any of you ever heard Festo, they're a German company that's been making really great advances in soft robotics and robotics in general lately. The most recent video I saw was like a seagull-shaped drone flying around a room this side, like a drone shaped like a seagull. Their bread and butter is making really good pneumatic valves and actuators. And now they're trying to replace their pneumatic valves and actuators with electric linear drive systems. So that's what this right here is. We look to them. So this is running on a stepper motor, and it can move its linear actuator portion really quickly, like back and forth. So it can replace, and it's designed to directly replace some of their pneumatic actuators. So cool. So we got that, figured out how to control that and have that connected basically to a bellows. This is a custom bellows that we made ourselves that squeezes. And then that in turn is then connected outwards to another soft actuator. So it's a soft actuator driving a soft actuator. And the volume of this bellows dictates exactly how big of the actuator it can drive. These actuators, not only can they go quick, but they can produce a lot of force. So we can, on paper at least, get up to about 100 PSI, we think, with this sort of system. I burst this bellows way below that. So we're not there yet. But it is capable, at least on this back end of that. And the whole thing is filled with oil, so it can go full ocean depth, as far as I can tell. And in the back, because we are changing volume here, we have to make up for it with a gland in the back. So as this thing is pushing back and forth up in front, the gland in the back is also moving at the same time. So it looks a little wild. What I'm not showing here is the control board for this, which is a little circuit board roughly about that large, has to go into 1 atmosphere housing. That's an Ethernet device. So you just need an Ethernet router, and then you can plug into any vehicle that has Ethernet connectivity to run it. It's just an IP address that you talk to. And we're getting towards joystick control with that. So I'm going to talk a little bit more about this over the next few slides. I have a funded project from the Schmidt Ocean Institute. Schmidt typically funds just ship time, and then you're supposed to come with your own stuff. But in this case, I have a project where they're actually funding some of our development work too. And with that, we got 2 cruises. I went on a trip a couple weeks ago that was about 5 or 6 days long off Hawaii, basically a warm-up round. We got to try out all kinds of new toys, including this drive system right here on their ROV. That's their ROV Sebastian, the 300,000 lumen Offender. But it's an awesome vehicle. There's just so much real estate around it for expansion. And the ROV team is just, I don't know, I learned a lot from watching them and how they operated. It was really neat. So really great vessel to operate on. Anyway, so we had this short trip, and then we have a much bigger trip I'll talk about in a little bit next year that we're leading up to. So we installed this on the front of their vehicle, and connected here is an actuation, some kind of actuator. So in this case, we had some folks from Harvard out, so they brought some of their actuators. So we just can plug any soft actuator you want into this thing. It's just a CPC quick disconnect that goes into it. And I think we have some video showing how it goes. So in the lab, you can kind of get an idea of how quickly now we're able to actuate. If you pay attention, these fingers are a little bit different than the last ones I've been showing. They actually actuate in 2 stages. They push, and then the distal end will actually push open, which is pretty neat. So we're doing a lot of the same stuff we've done before, which is grabbing and torturing sea life. But we're able to do it a lot quicker, which is pretty neat. Picking up things like xenophyophores. This is a single-celled animal that's super delicate. And then here comes the torture part. If we go up to something like this, we can grasp onto it. And then if you want, you can do that. So I know it's a little odd. There's not any real application, but showing that kind of actuation at speed, as far as I know, that's new. And so we have definitely some interest from NOAA and from the Navy in that, on how to apply that a little bit better. And we're going to stick a joystick onto that too, and make this so that if you want to have multiple channels, essentially you're going to stack up multiple versions of this, right? You just kind of have those stacked up. And this is fully scalable too. This is, I think, the smallest linear drive actuator I could buy from them with that kind of length, and they make them much bigger. So we're thinking big. We're thinking about making these maybe 4 or 5 times as large, getting up to like the 1 liter volume.
Is there a haptic option for this?
Potentially. Interesting thing about haptics is that they're awesome, but with soft robotics, in my opinion, you don't really need them. The whole point is that because it's compliant, you don't have to worry about how hard you're squeezing it. You've already figured that out ahead of time. So you could have haptics. There's a few ways to cut that, but I kind of like the idea that it's so simple. You can grab without that. So not yet. All right, so I can hopefully skip past that. So that trip we just did, if you want to learn more, here's the web link, or you can just go to schmidtocean.org. If you're a deep sea junkie like me, you've been there before, and they just have one of their cruises is called Designing the Future. And that trip, this is a great segue to the next segment. This image you're seeing here, I'm going to talk a little bit about it. The next trip we have with Falkor, with the Schmidt Ocean Institute at the end of 2020, is applying this system right here. But we're not ready to do that. So we did the soft robotic stuff this last trip. And next year, we're going to do more with this thing I'll tell you about. So that falls into the theme of 3D printing. Everything you just saw here is 3D printed. And so the idea is applying 3D printing to deep sea applications. I'm sure people in this room have already done this, but I'm going to go off the rails a little bit. So in this image right here on the front of Sebastian, we're setting up, you can see the hydraulic system I just spoke about, but there's a lot of 3D printed parts on this vehicle right now for this die. We got the drive system, deep sea soft actuators that have molds that were 3D printed to go into it. And then up here, this little part, I'll go into in a little bit, there's some cameras that are 3D printed. And then they're attached into some artwork that is also 3D printed. So there's a lot of plastic fantastic on there. But the coolest thing I think that we've made so far using 3D printing underwater is this system called the RAD sampler. So I did this, this is also stemming from my postdoc work at Harvard, but Schmidt has funded us to go much further with it. Let me play the video. Yeah. This is meant to, you'll see it kind of actuate a bit. This is meant to advance the way we can sample midwater animals. So ROVs like Ventana or Sebastian or any of these vehicles that are going down to study the midwater generally catch animals like this jelly using jars with a top and close that close together. The idea here is to make something that can reach out and grab it and be able to move that around with a manipulator arm. And so I collaborated with Zito and a bunch of other people at Harvard. He's an origami roboticist. That's a real thing. And he thought a lot about this geometry and how to make this work. We went from a very small scale thing to something very large, figured out how to make it work underwater. And as we can see here, we've gone down, this is with Ventana and Mbari in collaboration with them, and captured a whole bunch of animals. So that's cool. Great. So I have to keep looking ahead because I haven't done this presentation all the way through yet, and I can't see what's coming there. So that's cool if you can encapsulate an animal. That's all we're doing right here. Then what do you want to do with it after that is the sort of obvious question. What's great about that? So where we're going with this, and this is what we're trying to do next year with Schmidt, is we're trying to put cameras on these panels. Okay. The idea is that you can encapsulate something that's super delicate that really no matter what you do, you're going to destroy it on the way up. Instead, let's get some really good in situ imagery of it. So, and that idea, we can get some morphology out of it. And then, okay, what if we get the morphology, then we can grind it up, suck it up, get its DNA. We got the DNA, got the morphology. Maybe we can describe these species that are just too delicate otherwise to bring back up to the surface. That's quite contentious, right? Deep sea biologists, pure deep sea biologists will say, no, you need the holotype. And say, no, but there's no way you can get it. So the idea is to sensorize this thing and insert a suction system into it so that we can start doing some really contentious things, but hopefully describe new animals underwater. So that leads to the question of how do you put cameras onto these arms? There's 5 arms on this design right here. How do you get a camera onto here and here when all the deep sea cameras you can at least buy off the shelf that are in high resolution are like Coke cans at the very least, right? And they get much bigger if you want good optics and that sort of thing. So that question kind of bugged us. And I went out and obviously looked around and couldn't figure it out. And so we made our own. And so the past year, a lot of my work has been focused on this system here called DPI. Some of the first people to see it, but the paper just came out last week about it. DPI is a play on Pi, like Raspberry Pi. So it's a deep sea camera based on a Raspberry Pi computer and camera. So everything about that is affordable and open source, right? Python is what controls this thing. And the main focus on it was really the geometry of the camera here. So you can kind of see in here, who's worked with a Raspberry Pi camera before? Not that many people. One person raised their hand. So that's fine. This is a cell phone grade camera. So it's like really tiny, something flat that would fit into your cell phone a few years ago because you can't get your hands on what's in the iPhone 11 right now. And that's attached onto a small circuit board, does a little bit of onboard processing into H.264. And then that comes off of this ribbon cable into a Raspberry Pi computer right here. These are $10 computers that run Linux, a full-blown Linux system. The SD card then ends up costing more than the computer does with that. So DPI has its own as a camera and then a podded, this is podded, it's so clear it's hard to tell, but it's a podded computer. And we've tested this thing down to at least 5,500 meters in the lab. And in a minute, I'll show you, we sent it down, over 1,000 meters in the field a few times. So I haven't gotten down that deep in the field. It stops at 55 because I blew up the pressure tank before it kept working. But I actually don't know what the full implosion depth of this camera system is. So to do this camera design, as I was telling some folks over lunch, there's no way to make a deep sea camera or a camera in a pressure housing without maintaining the optics portion in air. Because if you fill it with oil or anything else, you're going to violate the optics that are designed around the medium that it's in, right? If you don't want to get into designing your own lens system, let's not go there. We just want to maintain a little bit of air right around this. So this whole design is set up to minimize the amount of implodable volume and make that right around that little tiny lens structure that's on there. From the side, it looks like this. We're 3D printing these shells using an SLA printer. I'll explain that in a minute. And I kind of call it, I call it a hybrid housing. You have a shell that's 3D printed. That's everything here in gray is the 3D printed portion. Then you lay in the camera, which is a little hard to see, but you can kind of see the circuit board here and the optics portion up here. And the inside geometry of this guides the level at which you fill up the epoxy, so that everything is potted except for this little portion right here, which is that optics assembly. And then we lay a glass disc on top. I found these $20 borosilicate discs online. They're polished, ready to go. And we can 3D print the O-ring seal as well using this type of printer. So there's no post-machining. It just comes right out of the printer, pop off the supports, and we assemble them, and then fill it up with potting. So the air gap is this little portion right here. So that minimal implodable volume is what does it. According to a few different ways I've gone at it, this 1/4-inch borosilicate disc should pop, given the way it's supported, somewhere around 35 or 4,000 meters. And I think the reason it doesn't is because everything around it's so plastic that everything just sort of deforms and it floats. That's the best way I can describe it. And so it kind of violates a few rules about the FEA on this thing. I think just because it's like freely supported. That's as far as I can say right now. We just kind of went at it and it started to work, which is pretty cool. So we filed a provisional patent on that. Even though we filed that, I'm trying to figure out how to handle this because I think I've gotten a lot of interest from people who want these cameras. So if you want one of these cameras, I'll give you everything if you're an academic or educational purpose. I'll give you the SLA parts, I'll give you the code. The code is already online on GitHub. It's not that complicated because it's Python stuff. It's freely available already. But if you want to make these shells and everything, I'll tell you how to do it. And the paper kind of describes it. The patent is there in case a company wants to license it. So it's an SLA 3D printer. Yep, so that's a photopolymer. I'm actually going to talk about that in a minute. No, it's fine. Yeah, one thing important about it is it's a totally solid material. Oh yeah. So applying these tiny cameras. Okay, so one thing I like to work with are BRUVs. BRUV stands for Baited Remote Underwater Video System. They look like a lot of different things. It's basically a video camera with some bait and a drop weight. And it's a system that can be used on a very small boat to go out and explore deep sea biodiversity. If you're into sharks, it's a great way to attract sharks. National Geographic uses these things. I make my own BRUVs. They're very straightforward. There's an acoustic release, a payload section, and then a float that goes onto it. I don't go any further than that. So in this little section here, I got some lights and a DPI system. This is the first time we did it off Bermuda, a couple camera heads. I had not potted the Raspberry Pi yet, so I actually did it. This is a 3D printed end cap. And that goes into this 1 atmosphere housing where the Raspberry Pis are inside. And sent it down. And another, yeah, sorry, the video's coming up. Another trip we just did last month, we used these cameras here on a larger payload system that had a large battery and some lights and a fiber optic connection to the surface. This is my winch I have at URI to guide camera grabs in Baltimore Canyon. So we were collaborating with Roxanne Beinart at URI, who's a deep sea biologist. She wanted to collect these chemosynthetic mussels that are in Baltimore Canyon. Larry, you probably know about this mussel that's over there. It's huge. And so we want to use the camera basically to guide where that grab happens. The next step we did with this, again, this is all about breaking rules. Here's your printed Raspberry Pis. Each of these Raspberry Pis has a Wi-Fi antenna on it. And so inside this 1 atmosphere housing here is a Wi-Fi router with a directional antenna. And so we're networking into these cameras with live video, doing Wi-Fi over a very short distance underwater, 3 of them at a time. So we have like live feed with 3 of them up with that. So Wi-Fi does actually work underwater over very short distances, especially if you use a directional antenna. So that was kind of a nifty thing to do. So now I think I have a video that shows both of those, Bermuda and that drop at the end for doing benthic get grabs. Take a sip of water and I'll walk you through it. So Raspberry Pi cameras now, the version 2 that you can buy, they're about $29. It's HD, but it's like gamer HD. It's not great, but it's okay. It's certainly better than any of the like Coke can standard definition cameras that you can buy right now that are about that size. So it's decent. Take away color. Color is lost a little bit. It's not so great. I think it could be increased with a little bit better lights that go with it. And it's not so great in low light. So those are some problems that we have with it. But we're basically tracking what technology we can buy ourselves and have open source code to it. If you want a really good camera like your cell phone, like what I have here, right? This is an amazing camera, but LG will never let you have access to that. So, and they're competing with iPhone and all that. So it's such a high competition space. So I know that my design could apply to much better cameras that are out there. We just can't buy them yet unless you buy them in high quantity. So this is a 6-gill shark. It's kind of cool. I slow down the eye staring up at you. Just kind of neat. He's mowing down at some bait that's going on right here. So it's pretty neat. And then the next of that, sorry, this goes on for a little bit. Yeah. So this is a Smith Mac grab where you're going down and grabbing mussels in a mussel bed using these cameras pointing straight down on there. So that's just a view of that. One cool thing is that the cameras are so cheap, it's no big deal if they break. I can just swap them out and I just go to sea with a bunch of them and make them up. So it sort of gets into expendable tools with that. All right, so you asked about the 3D printer and the material that's being used for that. So not all 3D printers are equal. And my printer of choice is a stereolithography printer, or SLA, as the lingo goes. Just to bring you into this, I'm going to talk about this printer a little bit more, so I want to spend a little time on it. There's a bunch of SLA printers that are on the market, but the best one right now is this Formlabs Form 2 and Form 3. This is right out of Boston. This company is down in Cambridge. It's like the iPhone of 3D printers. It's amazing. They cost about $3,000 and they're so worth it. They just work repeatedly. And I can teach a student in like 5 minutes how to run the thing. They're really, really great. They work based on the principle of photopolymers, which are liquid resins that when they're hit with UV light or some wavelength of light, they actually cure and harden. And so there's a print bed here that's full of resin, and then there's a laser on a galvo that's pointing around and selectively curing voxels inside that volume. And then it sort of pulls the print out of that bath as it grows, as it does layer by layer. Benefits of SLA printing is that they're ultra high resolution and very important to us underwater, they're completely solid parts. So this is their test part. They like to print this little rook here. This is what it looks like if you print it using a standard 3D printer that you're probably used to using called a fused deposition modeling printer, or FFF if you don't want to violate some trade laws. So the standard printers you probably are used to using look like hot glue guns in a gantry, and they're laying down melted material as they harden. And they leave all these artifacts, right? These ridges and bumps and a little bit of like hot glue traces into it. And they're not fully sealed. Water can intrude and go through these layers. An SLA printed version is in higher resolution, doesn't have all this stringy stuff that hangs off of it. And it's completely solid. And so we can use that to our advantage underwater. And I keep saying this, it uses a liquid resin bath. We'll come back to in a minute. That means that the printer has to be kept level. So because we can print completely solid materials, one of my students last year worked hard on printing a pressure housing design. I said, why don't you just try it? And he went for it, and he did it. We can print our own O-ring seals, right? I said I was already doing this with my little tiny cameras, so he decided to make a spherical housing. And he's making it here. We threw a few sensors into it, and this thing went down to 200 meters. That's where we tested it. And I think it can go much deeper. but we didn't want to implode it on that day. So that was a really cool early success. Yes, we can print pressure housings. We can do it repeatedly. I have a class I'm teaching at URI right now to sophomores, and they're learning about SolidWorks and they're learning about 3D printing, and their final project is to make their own pressure housings. So I'm testing this out with them. I have a dozen groups, and next month we're going to try out their housings. We're going to put them in a pressure test facility and see how repeatable the process is. So we're already getting there to the point where this sort of democratizes the idea of making underwater housings, right? If anybody's ever tried to make their own underwater deep sea instrument, they go, I'm going to need titanium or stainless or aluminum. I'm going to have to draw that up, and I'm going to need someone special to design that for me and then machine it. That's going to really limit me. It's going to stop me because I'm going to have to make this thing. It's going to cost a lot of money. We can print our own. That's pretty neat. That's super empowering. And my students can do that too. So that's exciting. Their work from last year, this is a senior project that did this, is in revision for additive manufacturing. So now I challenge the audience to answer the question that's cut off here. What animal or plant can you think of that makes its own pressure housing? Spheres are cool, but we can make spheres. You don't have to print a sphere. We can manufacture a sphere. What can we do with a printer? Where I'm going with this, what can we do with a 3D printer that we cannot machine ourselves? And that led me into this idea of a bio-inspired pressure housing. And then I started to ask myself this question. Got it. That's the only one I can think of. The chambered nautilus. It's a pretty cool animal I've been learning a lot about lately. There's a lot of papers from the early 80s about this animal. Chambered nautilus is famous because it has the golden, or close to the golden ratio, in terms of how these different segments of its shell are grown. The whole point biologically is that this animal doesn't have to change its shape as it grows. It just keeps expanding on these chambers that it produces. And all of these chambers here in this cutaway are full of air, or some kind of gas, I should say. I don't know exactly what it is, when the animal is underwater at depth. And it turns out that most species of chambered nautilus actually only exist at depth for their entire life cycle. Most of them can't go into shallow water, into warm water, and they can go as deep as 800 meters. So this animal lives in the depth range. It never actually comes up all the way. Most of them don't. There's one species that comes up a little bit shallower. And they've also been around a really long time, like 500 million years. So that's really interesting. An animal that's been around this long that had to evolve to create a pressure housing, and it looks like this, not a sphere. So I'm still not quite sure where this project is going, but I got a little bit of money to work on it. And so what we're doing is we're learning a lot about the chambered nautilus, and then this video won't play. I already tested it out, but we've 3D scanned the shell, and then we've done a bunch of SEM work on the outer and inner shell and on the cutaway, right on there. Oh, now it's playing. Interesting. To learn a little bit about how this animal is made, and then trying to print ourselves our own housings based on the chambered nautilus design. And I got to stop there. I can tell you we've done a little bit more work than I'm going to show here. You just have to be patient. I'm hoping in a year we'll have a lot. So I know it's frustrating, and we'll then be soon. But we've made progress with this. So I mean, some of the things you can kind of get into, we can print the housing, we can expand it. There's also a ceramic material that you can print with that we're playing around with a little bit. Ceramics can go super deep. So I'm happy to talk offline a little bit more about this project. But that's the whole idea, is to use the printer to make something that you couldn't normally make. We wouldn't be able to achieve otherwise. Okay, cool. Now what if you want to do this offshore? I go offshore. What if you want to take all your engineers and all these really smart people onto a boat and go out there, and everybody has all these ideas, and you go, oh, we can't make it here. We should have made that before we came. Let's take the printer to sea. An early project, I'm a co-author in this one, and other people have done this now. Falcor, the RV Falcor has one of these printers just nonstop on their boat, always running. But we were the first people to publish on it, at least. Took a FDM printer, that's that standard hot glue going on a gantry printer, took it offshore and printed some soft actuators on the fly. So they would go down on a dive, try it out. Pilots, engineers would talk. They say, you should probably make it this shape. Okay, I'll print overnight. Went back out and went through that a bunch of times. So they did this workflow. This printer works fine, doesn't need to be stabilized. It just goes. It's great. So FDM works without stabilization. If you remember, this printer I talked about earlier, the SLA printer that I like, has a resin bath. That's a liquid resin that has to be kept level, if only for spillage. But the form printers, at least, have sensors in there that will lock it out if it's out of like a half a degree. So, and we tried to replace that. We can't replace it. It's on the motherboard. You have to keep it level. So this pressure housing I actually showed earlier was actually printed at sea. And a senior group that I advised last year made this passive gimbal stabilizing system. They modeled the weight of this thing and figured out what the counterweight should be below it, how big this thing has to be. They looked into the bearings so they were really super smooth so that it wouldn't hold it up. And they went on 2 cruises. It's really easy to get spots for people on a cruise when you're not trying to put anything in the water. So they went out and they tested it out, and this thing works at sea. It's great. So we are now there. Yeah, so that housing that I showed you was printed at sea and then sent down on the CTD to 200 meters. And we didn't go any deeper because nobody wanted to blow something up on the CTD. Fair enough. But we're already there, right? We're at this point where we can make deep sea stuff offshore and get it underwater within, you know, a day. And if it doesn't work, we'll try it again tomorrow and that sort of thing. So, it's a lot of fun with that. All right, that's about it I have for additive manufacturing and what I'm using it for. And so now we're into our Act 3, now for something completely different. This is a third, but an important project that my lab's working on that we're really focused on, which is the idea of fiber optic distributed sensing, which maybe some people in this room have heard of before. It's a lot of words thrown together. For those who don't know, I'll just kind of walk you through the basic theory of it. Fiber optics are essentially glass strands, right, that are like the width of your hair. And then they usually have some cladding on them so that you can't break it so easy on the outside. So that's sort of a cutaway view. There's a core, a cladding, and then whatever coating on the outside of that. And the glass itself, because it's optically transparent, is essentially a waveguide for light. And the smaller diameter that that glass strand is, the further the light will go. Up to like, you know, hundreds of kilometers, right? They're fiber optic cables that cross oceans with that. So light travels long distances through a glass strand. Along the way, as the light bounces inside that waveguide, it turns out environmental variables will actually cause that light to scatter back at you a little bit. Temperature changes will do it, strain will change it. And if you pulse the signal, you know when you started that signal and you're reading back the backscatter that comes from that, you can actually figure out where along that fiber that, that environmental variable was occurring, the temperature or the strain. Anybody's used an OTDR before to find a fiber break, it's the same type of principle. It's a very simple, very sensitive, instrument that's measuring light that's coming back at it at the speed of light, which is pretty cool. So that sets up this idea of nodes that are set up along the length of a fiber. Is this where my animation is? Yeah, they look better in Keynote. So it turns out you can buy these systems off the shelf now. They've been around for about 10, 15 years or so. They're expensive. This is the one that I'm working with right here. This is a Silixa XT-DTS. It costs about $65,000, and it's very big. It's like a rack mount system, 4U rack mount system with big handles and all that sort of thing. And that's its like most basic form. There are more advanced ones that are also big and bulky and that sort of thing. So our project is to get this thing to work in the deep sea underwater, because that box ain't gonna go on underwater on its own. This system, just to put a few other specs onto it, it uses Raman scattering. So there's different ways light can scatter. Raman is the lowest level of that and sensitive to temperature. Brillouin and Rayleigh are more sensitive to strain. That's a problem if you're sensing temperature. It's sensitive to both things at these ranges. So if you're sensing temperature and then you go up and you kick the fiber, it will also ring out a signal. With the Raman scattering, it's just sensing the temperature. So that's a pretty nice way to get around it. With Raman scattering, this system can measure up to 10 kilometers of a single fiber. It has 4 different channels, so it's 4 10-kilometer cables it can do. And it can measure a node every quarter meter. So 1,000 meters or 1 kilometer becomes 4,000 nodes, 4,000 temperature sensors in one fiber optic. So that's pretty awesome. So the idea is to make this to work underwater and apply it. So we're getting along. This is here. Sorry, in a minute, it's sort of a bad video, but this is all those parts rearranged in a jumble and then optimized inside a, a pressure housing. And there's a few other things we got to worry about. We're concerned about light transmission and loss. And so we have to minimize any losses through these bulkheads and all that sort of thing. So that's part of the problem we're going into. And we're also interested in what kind of sensing cable we should use in there. All right, so you might be asking why we want to do that. There's actually a range of applications for this. One reason that this is getting funded by the Navy, is the Navy is interested in resolving sound velocity profiles in high resolution, right? Density layers, where do we hide our sub, that sort of thing. So that gets into mooring and towed arrays of fiber optics, if you can imagine that. And physical oceanographers are also interested in this because they could visualize in real time in a synoptic measurement how internal waves and thin layers are moving past like a standing mooring of mooring string or something like that of that fiber. One thing I'm really interested in is applying this to seafloor venting. So I showed this here. It looks like I'm running out of time, so I won't have a chance to walk you through. But it's a really interesting paper where a team off the coast of Oregon and Washington at Juan de Fuca Ridge laid out 12 temperature sensors. So this is not fiber optic. They just put 12 separate temperature sensors around a diffuse flow vent site. And it turns out they left it there for a year. One of those sensors, one out of those 12, actually got a really good signal and showed that diffuse flow venting was paired with tides. And that comes into effect because the more water that's above a vent site, the more hydrostatic pressure is pushing down on it. So at high tide, basically, there's a little bit less venting. We can go a bit further. There are periods of volcanism that are tied in with Milankovitch cycles and all that sort of thing. But the tidal cycle is really interesting. And then you could also extrapolate this to sea level rise, right? Like what's going to happen when we add another 50 meters, and what's that going to do to venting in ecology? And that's something actually that I've worked on before. As a case example application, a few years ago when I was working on Nautilus with the ROV, we were out in the Galapagos Islands and we were working through a hydrothermal rift valley, and we started to notice all these skate eggs that were laid out along the length of that valley. And we went back and we measured the ROV's temperature that it was sensing wherever we saw those egg cases. And it turns out that wherever there's a little bit warmer water, that's where we found these skate eggs cases. So we made a case in this paper. This is a plot that shows the ROV's track. And wherever there's stars, there's more egg cases. And that's paired with lighter colors, which means a higher temperature, right? They seem to be collecting near a vent site. So these deep sea skates are actually putting their eggs near warm water to decrease their incubation time. And I was just learning by talking with Annie that that is also, it seems to be the case for deep sea octopuses, maybe. So there's all kinds of interesting biology questions. Imagine if we could lay out a nice fiber optic grid, right? This is where I want to do it. I want to do it at axial seamount where we can plug into one of these nodes and lay out a grid like this. Instead of having just one node that works, let's have thousands of them. And we can create a heat map, right? Let this thing cook for a year and see what happens. So that's what we're hoping to do with it. Yeah, so with that, I've finished my 3 topics that we're doing in the lab. We have a little time for questions, so thanks.
Oh, it's an easy one. I'm intrigued by the EK60 and the ROV issue with the scattering layer. Have you actually done the experiment of shutting the lights off and determining that it is the light rather than the ROV?
Yeah, so in June in the Solomons, and that project I was showing you, the problem is you can do it on an ROV, but the ROV is still producing noise. So you can't parse out the two. So we made up this payload that had a low light camera, an EK80 subsea, and dimmable lights. And we went through sequences and we raised it up and we lowered it. This is like a really quiet platform acoustically, right? There's no thrusters or nothing on this thing. And brought it down to different depths and ran the experiment. And even though we did our best to isolate the EK80 with power, you probably know where this is going, it still gave dirty data. And so every 10% increment of light, it's got a step change function in noise in the data. So it kind of failed. So we need to get a cleaner EK80 out of that. So we need to do it again. Yeah.
So one of the things that you said was one of your motivating factors was that ROVs are loud and that they produce a lot of light, but all of the instruments that you've showed us videos of today, you have introduced artificial light. So in kind of your vision for the future, do you imagine kind of cameras we're using will be thermal cameras, or do you see a possibility of actually eliminating the light from the ROV?
I don't know if we're ever going to eliminate it, but I can tell we can run around with a dim light. So one thing I didn't show today is some low light camera work that I've done where we've flown around with lights that are like dimmer than your cell phone light and on a big ROV, and you can see everything with the low light camera. It's a really nice one. It has 4 million ISO color and all that sort of thing. Camera costs 20 grand for the head itself, not including the housing and all that sort of thing, and it breaks really easily. And so, yes, at some point, we are going to be able to turn out the lights. And I do dream of a day when a camera like Dept will not need that much light to go with it. But we're really at the edge of what I can buy, or at the edge of what commercial technology is available to us. So I kind of went at this originally like a few years ago, like, oh, we're going to make this awesome vehicle that'll be totally quiet and blah, blah, blah. Actually, we have a lot of work to do before then. And it's kind of broken off into a few different tangents. The soft robotic stuff, though, that stuff is almost completely silent. So that I didn't totally connect that in this presentation, but if we have a full soft manipulator that's strong enough, we can get rid of the whole hydraulic power unit, and that would make it quiet.
You mentioned that wine bottle actuator could produce like 100 psi or something. What about the actual arms? What's like the max psi on that? Could you rip that, see an enemy off the rock if you really wanted to?
Sure, that's okay. It comes into the the question was for the mic, can the actuators themselves handle high pressure if I could produce it? And you can tune them for different pressures. It's actually fairly straightforward to do that, like making walls a little bit thicker, durometer choice or that sort of thing. And yeah, there's a sweet spot around 100, 150 PSI where they start to become, strong enough to, crack an egg and that sort of thing, maybe do a little bit more with it. And there's other groups that are making more progress with that. So I'm more interested in the drive system, and then hopefully I can connect with people who are already making those higher pressure actuators to go with it. Yeah, so we need to go a little bit higher pressure is the point, but we can get there.
Yeah, it'd be nice if you could do both with the 1, 2, like grab solid down a little bit.
Yeah, right now they're totally like divergent paths, right? You still need the big manipulator, and yeah, it can be a soft gripper right there for when you need it. But I think we're gonna get to the point where we can get away from the big metal, aluminum, titanium manipulators.
Oh, yeah. Hi, Brennan.
Hey.
Very nice talk.
Thanks.
I've experienced that SLA continues to cure if it's exposed to a lot of light. There's sort of some additional curing and deformation going on. So do you expect your camera housings to have a sort of finite shelf life and before they're swapped out, or?
Maybe. I mean, the way the form process is done, it's cured in the printer, and then you put it in a UV bath after that. There's like another cure unit. It's like a suntan booth, basically. And that cooks it really, really hard. And after that, it should be totally done. It should just get stronger, because there's like a curve, right? With light, with time, with UV, and at some point the material gets like really strong. And then what happens? Is it going to fail over time? I don't know. It's a good question. I mean, one answer is that if you put the camera underwater at depth, it doesn't get that much UV light to go with it. But if you do leave it out on deck over long periods of time, I don't know. I haven't seen it though. I have put a bunch of parts on the back deck of the boat, and I've been beating them around for a few years. And it hasn't been too bad yet. Yeah, it's definitely something to be watching out for.
On your mic. I was just wondering if I heard you correctly. I thought you sort of said your sample resolution to measure temperature with your fiber optic sensor was about 1 kilometer.
You can do up to 10, it says on paper. You can do 10 kilometers, but 1 seems to work a little bit better.
So you get a temperature reading every kilometer of cable.
No, you get a temperature. You get a full synoptic cable length temperature reading. And it takes, depending on the length that you're sensing, it'll take time for it to resolve that. It's like an RMS type of calculation. So 10 kilometers takes something like 2 to 3 minutes for it to sense every node and average them out and get a reliable reading. 1 kilometer is about every 30 seconds. You can pull the cable to get it that way. But it doesn't have to do it in discrete steps. It just shoots the whole fiber. Yes. Yeah. Yeah. So it's pulsing, waiting for return, doing it again and again, like averaging it out. To get a better reading. Yeah.
Okay, we're out of time.
Yeah, sorry, went longer than I thought.
Feel free to ask him if he's also willing to drink beer.